In this video, we're going to look at how enzymes lower activation energy by stabilizing the transition state. And so by the end of the video, I want you to be able to define the transition state of a reaction in regards to the energy states of a reaction. I want you to describe why it's important that enzymes stabilize the transition state of the reaction and not the substrate. I want you to be able to define binding energy and be able to understand and interpret reaction coordinate diagrams. All right, so here is a reaction coordinate diagram of a reaction. Now, this reaction here is not catalyzed by an enzyme. And what we have on the y-axis is free energy, G. On the x-axis, we have reaction coordinate. Here's our substrate by S. Okay, it has this much energy. Here's the product, P. It has this much energy. Remember, delta G is the energy of the product minus the energy of the substrate. If it is negative, it's an exergonic reaction, and sure enough, the energy of the product is less than the energy of the substrate, and so this reaction is indeed exergonic. And we have several things. We've got this right here. This is the transition state. And the transition state is a form of the substrate. It's the form that the substrate must take before it becomes product. And it is defined as the single highest energy state of the substrate. Okay, it's got to reach that before moving on to becoming product. So you have to invest energy to reach the transition state, but then you get all of that energy back. That's why it's called investing energy. And then you get more, right? Right here. This is the delta G, right here. That's the delta G. This here, right? This is the energy necessary to reach the transition state. It's the activation energy. And what enzymes do is they stabilize the transition state. They stabilize this state of the substrate such that it lowers the activation energy. Remember, when you stabilize a structure, you lower its energy state. And it's this transition state, it's this hurdle that the reaction has to get over that is going to determine the rate of that reaction. The more energy it takes to get to that transition state, the slower that reaction is going to be. So let's take a look at a hypothetical reaction. A reaction in which we have this metal rod, and the reaction is we're taking that metal rod and we're breaking it in two. But the transition state, in order to get from an intact metal rod to a broken metal rod, we need to bend it. And it's getting it into this orientation that's going to be our transition state. That energy leading up to that is our activation energy. And so what we want to look at is if we wanted to design an enzyme that will help us catalyze this reaction, allow us to more quickly break that rod, what do we want to design that hypothetical enzyme to stabilize? Do we want it to stabilize the transition state or the substrate? Well, let's look what happens if we design it specifically to stabilize the substrate. Okay, so now the substrate, essentially what we've done is we have made that rod even harder to break, even harder to reach the transition state because it's pretty happy right here interacting with the magnets here in our hypothetical enzyme. So if we take a look at our reaction now in the presence of this fake enzyme that stabilizes the metal rod itself, we have this. Instead of making it easier to reach that transition state, that bent state, we make it harder. We're stabilizing the substrate. So here's our enzyme substrate complex, which is stabilizing the substrate, meaning that it's even less energy than the substrate itself. So now, okay, great, we bind that metal magnet enzyme that we've made that's stabilizing the substrate. It's lowering the energy of that substrate. And now we have even more energy to get to the to the transition state. It's even harder to reach that transition state. So this can't be the case, right? Enzymes cannot simply stabilize and thus reduce the energy of the substrate. That would make that would make those reactions even slower. Okay, which means that what enzymes have to stabilize is the transition state. So if we now create this magnet enzyme that instead of stabilizing the substrate, it stabilizes the transition state. Okay, so it has some interactions with the substrate. It can bind the substrate, but it really stabilizes the transition state of that substrate. And again, when you stabilize something, you reduce the energy. So here's what that transition state would look like without the enzyme. And here's that transition state with the enzyme. These little bumps here, this is the transition state to bind the enzyme. And then this is here the transition state of getting that substrate into its transition state. And then we release the product. Okay, so this is a nice demonstration of how the enzyme must stabilize the transition state in order to lower that activation energy. Here is the activation energy from here to here without an enzyme, and here's the activation with the enzyme from here to here. Okay. So then we have our simple enzymatic reaction where we need that enzyme to bind the substrate. Okay, there's going to be a little bit of activation energy there. Then we need that substrate to get to convert to product. Okay, but it needs to reach the transition state. That's this bump here. And then that product needs to be released from the enzyme. That's this little teeny bump here. Okay. And it's this right here between the transition state, okay, of the enzyme catalyzed reaction and the transition state of the non-enzyme catalyzed reaction. This difference right here in the green arrow, this is called delta GB, or simply the binding energy, the difference in transition state energy between the catalyzed and the non-catalyzed reaction. It's the amount of energy that the enzyme reduces the transition state by. Okay, so now we have lots of awesome questions that we can ask regarding these reaction coordinate diagrams. I want you to pause it. I want you to take a moment. And I want you to try to answer each of these questions simply by looking at this graph. All of this information you can get right here from this graph. You don't need to read anything else. Okay, so I'll let you pause. Okay, I've assumed that you've tried to do this on your own. Let's do it together. So what is the energy of the transition state without the enzyme? That is going to be right here, right? It's not the substrate. It's not the energy of the product. That double dagger, that means transition state. And so the energy of the transition state without the enzyme is, is right here. So whatever that number is right there. Next, does the enzyme change the delta G? Okay, let's think about that. When we're looking at reaction coordinate diagrams, the best way to think about delta G is the energy of the product minus the energy of the substrate. The energy of the product minus the energy of the substrate. Well, in black is the uncatalyzed reaction. In blue is the catalyzed reaction. Okay, black without enzyme, blue with enzyme. So what we notice is whether we're talking about with or without enzyme, the substrate still has this energy right here. The product still has this energy right here. So the answer is the enzyme does not change the energy of the substrate or the product and therefore cannot change the delta G. And now that sort of brings us next to this question. Can an enzyme convert an endergonic reaction into an exergonic reaction? Well, we just said that it can't change the energy of the substrate. It just said can't change the energy of the product. And so that is the only way you can convert an endergonic reaction into an exergonic reaction, is by changing the energy of the substrate and or the product. We just saw that an enzyme can't do that. And so no, an enzyme cannot convert an endergonic reaction into an exergonic reaction. All right, let's continue. What is the activation energy with the enzyme? Okay, black is without enzyme. So here is the activation energy from here to here. So this whole thing here. And then with the enzyme in blue, you look at the highest peak here, and that's going to be that transition state peak. And again, from substrate up to the top here. So basically, you look at the energy of the substrate minus the energy of the transition state there. This is the energy of the transition state. And finally, what describes the amount of energy by which the transition state is reduced in the presence of enzyme? That's our binding energy. That's our green arrow here. That's the energy of the transition state minus the energy of the transition state in the presence of the enzyme. That is your binding energy. Okay, so again, make sure you review this. Make sure that you can define the transition state of a reaction in regards to the energy states of a reaction. Describe why it's important that enzymes stabilize the transition state of a reaction and not the substrate. Define binding energy, and then go through and be able to understand and interpret reaction coordinate diagrams when we're looking at reactions that are either catalyzed by an enzyme or not catalyzed by an enzyme, and look at the difference and be able to interpret those differences.